Hi, today we're going to be looking at Chapter 3, where we are displaying or summarizing quantitative data as opposed to categorical data. And frankly, we do this more than we do the other, although it's sometimes interesting to display categorical data. Frequently, there's not a lot that we can do in terms of heavy-duty analysis of it. We're more likely to do this with quantitative data, although there's some of both, and both are needed. So um, let's take a look. Some of this is going to be familiar to you from 7th or 8th grade, your math class. In fact, this very first one, that diagram was on one of my 7th grade pre-algebra tests. So with quantitative variables, there's no intrinsic way to make piles of data. With categorical data, it's already divided up into categories. We just divide everything into the piles and count how big the pile is. So usually we'll divide up all possible values into equal width bins, then count the number of cases that fall into each bin. When you do that, this is called a histogram. It displays the distribution at a glance by using bars whose bases are the bin values and whose heights are counts. So with the histogram, one of the things that comes up is, well, how big do you make the bin width? Well, this is part of the art of displaying data well. If you do too few bins, then it doesn't really give you an idea of the shape. If you do too many bins, you have something that's hard to look at and it still doesn't give you an idea of the shape very well. So this one is one where someone is throwing with their left hand, their distance from the bullseye in inches, and how frequently they got that. This person is actually pretty good. And I'm assuming they're throwing darts. So a couple things to notice. One is there are no gaps in a histogram unless there is a gap in the data. So on this one, it doesn't say it, but since it says these are equal width, we know that this is 1.5, for example. And then here we know that this is 10.5. Between 10.5 and 12, he never got that distance. That's why there's this gap in the data. Now, if we do it instead of frequency, we can do relative frequency if we replace this with percentages. But much like we found with our categorical data, that when we replace it with the relative frequencies, it doesn't actually change the shape. It would just change the what you have over here on this vertical column, provided, of course, that you didn't change the bin width. So in tonight's reading assignment, you'll learn how to create a histogram using your calculator. It will automatically create one for you, given certain, if you put in the data. You can also force it to have certain bin widths and all that kind of stuff, and that'll be in tonight's reading. So I think that's like a histogram, but has certain advantages, is a stem and leaf display. And if you called it a stem and leaf plot, I'm not going to make a federal case of that. I don't know why I always want to say that, but it's a stem and leaf display. It's like a histogram, but it has one advantage, and that is that you don't lose any of the original data. All the original data is still there. Your book says that they're especially useful when you make them by hand for batches of fewer than a few hundred data values, and I almost spit the bit when I read that. It's like a few hundred. I was thinking if it was, more than about 30, it would be crazy to make a stem and leaf display. But, they have more experience than I do. I just don't want to do it. Again, this is an example taken from a pre-algebra worksheet with the weight of each girl on a basketball team. And again, notice there's no title. There's no explanation of what the heck this is. We always want to be giving context where we can. So this is going to be players' weights. And in this, we need to somehow explain, well, what does this mean? So when you have 10/6 is 106 pounds. On this one, most people could have figured it out, but occasionally you have ones where it's a little bit more complicated. Notice on this one, the smaller units are at the top. Most stem and leaf displays have the larger units at the top. The one thing I like about having the smaller units at the top is all you have to do is rotate this 90 degrees counterclockwise, and you've got a histogram, which is pretty cool. Also with these, sometimes if you have a lot of data points, instead of dividing it up by tens like this, I'm going to draw this down here. You don't need to if you don't want to. But we could divide it up, that 12, into two separate parts. So we could do like the high tens, so 106, and there would be none in the low hundreds. We could do one in the higher 110 pound range. There'd be one in the lower 110 pound range. There'd be one in the higher 120s, three in the lower 120s, none in the higher 130s. And I'm out of room, so I'm going to stop. For this one, that's probably not necessary. This is a little bit like having too many bins in a histogram. You're chopping the data up so fine that many of the bins only have one item in them. But again, if you have a whole bunch on here, you have a list of 15 or 20, it may be a good idea to split it up into finer pieces. They'll also talk about the fact that sometimes if you have, like if you're, I think the example that they use is something about measuring the weights of cattle. You know, if you have a 1,348 pound cattle, a lot of times that gets reported as 13/4 or 13/5, and they just chop this off and throw it away. Because, you know, in that big an animal, a pound or two either way, nobody really cares that much. Another plot, and this is one that you have not probably seen before, is called a dot plot. Here it just places a dot along an axis for each case of the data. Like a stem and leaf plot, the dot plot preserves the original data values, but they're not grouped into bins. So this is only for individual data values. So if we look like right here in the middle of this, this is the fuel economy for a random sample of 215 model year vehicles. All of these got 31 miles to the gallon. These are 32, these are 30. Some tiny Honda Civic got 40 or something. I have no idea. That may have been an early Prius. Who knows? But it preserves the data also. Occasionally dot plots are nice. They do show shape nicely, but you have to have a lot of data values before they really work well showing you the shape. Now, with these three, you have to have quantitative data. And frankly, of the three, we're going to use the histogram more than any of the others. I just realized that this should have been a dot plot, not a box plot. We'll talk about box plots in a moment. But they have to be quantitative data. Okay? If your data is not quantitative, then you cannot use a histogram. You can use a bar chart, but you cannot use a histogram. All right, moving on to page 2. Histograms are great if they're done well for being able to explain the shape of a distribution or describe a distribution. This is going to be on the AP exam in all likelihood. I've looked at several past AP exams, and they'll give you a distribution, and they'll ask you to describe it. So there's 3 things you should talk about: the shape, the center, and the spread. Let's talk about shape. There are 3 different things we're going to look at with shape. First of all, and this is one that you can see easily from a histogram. You can see it easily in a dot plot and in a stem and leaf display. Whether it is unimodal, bimodal, or multimodal. So unimodal is the ones that we'll see more often than anything else, where you have one bar that has more in it than any other single bar. And that's true here too, but there's 2 that are much higher than everybody else. This is bimodal. And here we have multimodal. We have lots of high spots and then low spots. Okay? A histogram that doesn't have any obvious mode, all the bars are about the same height, is called uniform. And if you go down to the end of your page, this is considered uniform. And, when we say uniform, we're not saying it's perfectly uniform. Just like if you look around the room and look at everybody's uniforms, they're not all exactly the same, but they are all pretty similar. The next thing we look at is symmetry. And symmetry, you understand the idea of symmetry. For example, your body is basically symmetric. The left side and the right side are pretty close to being exactly the same. There are some things that are different. Your heart's slightly off center. Your liver is further on one side than the other. You may have a finger that you broke, and so your left hand and your right hand aren't perfectly symmetrical. But we're just talking about, is it basically symmetric? So if it's basically symmetric, what you'll be able to do is draw a line right down the middle, fold it in half, and the 2 halves will match pretty closely. So for this one, if we were to draw a line right here through the middle and fold it in half, the 2 pieces would look pretty similar. They're not exactly the same, but they're pretty close. So when we say symmetric, we're not saying exactly symmetric. We're saying, it's pretty close. Okay. Note that this one also happens to be unimodal. You can have symmetric distributions with bimodal and multimodal, but it's way harder. It's less common. Unimodal, it's easier to have symmetric distributions of data. Now, the part at the ends of your data are called the tails, and they're usually lower. That's part of why they're called the tails. And if one end stretches out further than the other, the histogram is said to be skewed to the side of the longer tail. People sometimes get this mixed up, and I did, honestly, for years. I thought it was the other way around. And I mean for years. Like, I got this 2 or 3 years ago when Mr. Hedstrom and I were talking about it. I had it backwards in my head, and I think a lot of people do. So for this one, for example, this is the relative frequency of yearly income in thousands of dollars. That's one that, even if you didn't see this, you would guess that it would be right skewed. There's going to be a lot in here, and then there are going to be fewer and fewer and fewer people who make lots and lots and lots of money. On the other hand, this one, and this one's not nearly as well labeled, but this is the mortality rate by age of, I don't know if it was a state. It's certainly not a country. That's not enough people dying unless it's a pretty small country. And this one is left skewed. This one, at first I was like, what the heck happened here? Well, infant mortality is still a thing. The infant mortality rate, more children die from the time they're born to the first year than, well, you got to get up to like 50 something before you have anything like that again. So in this particular example, this is left skewed because the tail goes to the left. All right, and again, here are some examples. This one is actually, again, out of a middle school book. This is symmetric, and it is bimodal, sort of. This one, it's not strongly bimodal. This is skewed specifically. This one is left skewed because the tail runs to the left. This is a single peak. We usually say unimodal rather than single peaked. But if you said single peaked, people would know what you were talking about. Double peaked, this is bimodal. And as I showed you before, this is something that would be considered primarily uniform. It's not perfectly uniform, but the shape is basically uniform. That brings up one thing real quick before we go on to page 3, that my instructor from the week-long summer institute I attended online said, make sure your students use a lot of LY words. It is basically uniform. It is nearly uniform. Those kinds of things. It's not perfectly uniform, and we all understand that. All right. Page 3, we'll do a little bit of this. So, do any unusual features stick out? You've talked about outliers before. Remember, outliers are ones that are way off from the rest of the data. For example, if we were to make a histogram of the ages of the people in the room, well, there's going to be an outlier. Since I'm not there today, it's your substitute. They're an outlier. Their age is much different than your ages. So with outliers, it's interesting. An outlier can be the most informative part of your data, or it might be just wrong. Now, how could that happen? Well, maybe someone dropped a decimal point, and it's way bigger than it should be. Or 2 of the digits of a numeric value got transposed. Something went badly wrong. Sometimes that's what gives you an outlier. Sometimes the outlier tells you, well, okay, this is a histogram of weights in grams. It's like, why does this one weigh so much more than the other ones? Well, I don't know. But I'm interested in finding out about this. When I see an outlier, I'm like, why is there an outlier? And you should be too. Why is there an outlier in this data? On this one, this is a frequency and age. And it's like, of what? Okay. I'm assuming, given the ages here, that this is people. But frequency of what? I haven't the slightest idea. This is why it's so important to have a title on your graphs so that you get some of the context out of that. So here, this is pretty clearly an outlier. This, well, there's a gap, And you should talk about gaps when you have them, when you're describing a distribution. Remember, it's shape, including unusual features, center, and spread. So if you have gaps, that's part of the shape. You should talk about that. This, is it an outlier? Maybe, maybe not. We'll talk about a rule of thumb for outliers a little bit later. Part of the problem with it is that not everybody uses the same rule of thumb. And that's okay, but it's important to identify, well, there may be an outlier in the range between 90 and 100, but then again, maybe not. All right, we will pick this up here on Friday when, God willing, I will be back here with you. I miss you. I hope you do well on today's quiz, and I'll look forward to hopefully seeing you on Friday.